Ever stop and think about what connects you, the device you're watching this on, and the most distant star in the galaxy? Well, it's the exact same stuff. Today, we're going to deconstruct that stuff, the atom. It's the fundamental building block of literally everything.
All right, so here's the plan. We'll kick things off with the basic anatomy of an atom, then figure out why they just can't seem to stay single. What's their drive to bond? Then, we'll journey through time to see how our picture of the atom has changed, and we'll wrap up with the mind-bending modern quantum view. Okay, let's dive in.
First up, anatomy of an atom. So what are we all made of? Really?
So, what exactly is an atom? Think of it like this. It's the smallest possible piece of something that is still that thing. You can't break down an atom of gold any further and still have gold. It's the basic, fundamental ID card for every single element.
Okay, let's meet the team inside the atom. You've got three main players. In the center, the nucleus, you'll find the protons. They're positive, and the neutrons, which are, you guessed it, neutral. These guys are the heavy lifters. They have almost all the mass. Then, zipping around the outside are the electrons. And look at their mass. They're teeny tiny, almost 2,000 times lighter than a proton. But here's the kicker. Their tiny negative charge perfectly cancels out the proton's positive charge. That balance is, well, it's everything.
And this is where things get really weird. An atom is more than 99% empty space. Yeah, you heard that right. To put that into perspective, if the nucleus of an atom was a tiny marble sitting on the 50-yard line of a football stadium, the electrons would be like little specks of dust flying around the nosebleed seats. Everything in between? Nothing. Just empty space.
Okay, so that leads to a pretty obvious question, right? If you and your chair are both mostly nothing, why aren't you just falling through it right now? Well, the answer is all about forces. The electrons whizzing around your atoms are negatively charged, and so are the ones in the chair. And what do like charges do? They repel. It's like trying to smash the same poles of two really strong magnets together. You can't. That powerful repulsion is what we feel as solid.
All right, next section, the drive to bond. Turns out atoms are not loners. They're actually super social. So let's figure out what makes them want to pair up.
And really, it all boils down to one simple idea: stability. Atoms, just like everything else in the universe, want to get to the lowest, most stable energy state they can. Think of a lone, reactive atom as being like a ball perched right at the top of a steep hill. It's full of potential energy, it's unstable. Forming a bond is like letting that ball roll to the bottom. It settles down, it becomes stable.
So where does all this action happen? Well, it's not the electrons buried deep inside that do the mingling. It's all about the ones on the very edge, in the outermost shell. We call these valence electrons. They're basically the atom's hands, reaching out to interact with other atoms. How many of these valence electrons an atom has pretty much defines its entire chemical personality.
And what's the ultimate goal? What does every atom aspire to be? A noble gas. Well, sort of. They want to look like a noble gas, with a perfectly full outer shell of electrons. We call this the octet rule. It's like the VIP club of the periodic table. And atoms will do whatever it takes, gain, lose, or share those valence electrons to get that full outer shell and reach their version of atomic nirvana.
So how in the world did we figure any of this out? I mean, you can't exactly see an atom. Let's take a look at how our picture of it has changed over time.
Yeah, this definitely wasn't a single aha moment. It was more like a scientific relay race over 100 years. Each scientist built on the work of the person before them, fixing the old mistakes and, making a few new ones along the way, but always getting a little bit closer.
First up was John Dalton, way back in 1803. His big idea? He thought atoms were just tiny, solid, indestructible balls, like miniature billiard balls. A great starting point for sure, but the big flaw was thinking they couldn't be broken down any further.
Then J.J. Thomson comes along and discovers the electron. So the billiard ball idea was out. His model was called the plum pudding model, or think of it like a chocolate chip cookie. The cookie dough is a big blob of positive charge, and the negative electrons are the chocolate chips scattered around inside. A huge step forward because it showed atoms have parts, but it was still missing something major.
And that something was the nucleus. Ernest Rutherford figured this out in a brilliant experiment where he basically shot tiny particles at a super thin sheet of gold foil. He expected them to go right through, but some of them bounced back. This told him all the positive charge and most of the mass was packed into a tiny, dense center. So now we have a nucleus. But this created a brand new, massive problem. If opposites attract, why didn't the negative electrons just spiral into that positive nucleus and boom?
So along comes Niels Bohr with a really clever fix. He proposed the planetary model. His idea was that electrons could only exist in very specific orbits, like planets stuck on tracks around the sun. They couldn't be anywhere in between. It was a brilliant idea that perfectly explained the hydrogen atom, but it was kind of a cheat. It totally violated the rules of classical physics, which said an orbiting charge must lose energy. So the model worked, but nobody really knew why.
And that's where the old way of thinking hit a brick wall. Bohr's model was the last gasp of classical physics trying to explain the atom. To go further, we had to take a quantum leap into a whole new, much weirder world.
See, for all its cleverness, Bohr's model had some serious deal breakers. It only really worked for hydrogen, a super simple atom. It couldn't explain chemical bonding, and it pretty much ignored the fact that electrons can act like waves. But the biggest problem? It went against something called the Heisenberg uncertainty principle, which basically says you can't know exactly where an electron is and where it's going at the same time. Bohr's neat little orbit said you could, and that was a problem.
And then, in 1926, Erwin Schrödinger came along and basically said, "Everybody, you're thinking about this all wrong." His idea was revolutionary. He said, what if we stop trying to picture electrons as tiny little planets at all? What if, instead, we treat them as waves?
And that was the quantum leap. We literally threw out the old map. Gone are the neat, predictable orbits of the Bohr model. In their place, we have something called orbitals. And they're not paths. They're more like fuzzy, 3D clouds that just show us where the electron is most likely to be at any given moment.
So think about that. We gave up on ever knowing an electron's precise location. The modern quantum model doesn't care about where it is, it cares about where it could be. These clouds of probability, these orbitals, this is the bedrock of our modern understanding of the atom, and it's the foundation for all of chemistry today.
And there you have it. Our journey from seeing the atom as a simple, solid ball to seeing it as a fuzzy cloud of pure probability. It's an incredible story of scientific discovery, of constantly challenging what we think we know. And it leaves us with a pretty mind-bending question to chew on. If the very foundation of everything solid in our world is governed by chance, what does that say about the nature of reality itself?